Hello students, welcome to this lecture. Today we are going to start our new unit, that is Introduction to State Space Analysis. In what is state space analysis, how it is different from the other analysis methods, okay, that is what we are going to see here. State space analysis. The earlier system modeling can be done through mathematical modeling or the transfer function modeling, correct? In the continuous domain, we got the transfer function. In the discrete domain, we got the pulse transfer functions. As we got the differential equations in the continuous time and the difference equation in the discrete time. Okay. Those are the different modeling of the system. Okay. And state space modeling is an alternative method of modeling of a system. Okay. It uses the state space modeling, it uses matrices and vectors to represent the system parameters and variables. In the control system engineering, the state space representation is a mathematical model as it uses the matrices and vectors. Okay? It is a mathematical model of a physical system as a set of input, output, and state variables related by the first order differential equations. That is very important. Okay? To abstract the number of inputs, outputs, and the states, the variables are expressed as vectors. Here in this case, the variables are expressed as vectors. Okay, vectors. Okay, and vectors can be represented in matrices. So, what is the motivation for the state space modeling? Is that it is easier to use or develop an algorithm to analyze this particular modeling, which computers can help us. Okay. Easier for computers to perform the matrix algebra because there are multiple computational softwares. For example, the matrices, the MATLAB. The MATLAB itself stands for the matrix laboratory. It does all the computations as with the matrices. Okay. The state space modeling, the advantage it can provide is that it handles the multiple input and multiple output at the same time. Okay, as we're using the matrices, okay, when we'll go into the modeling section, that you will get the idea of what is how it can handle the multiple input, multiple outputs. It provides more information about the system through the internal variables. What we call it as the states. States are the internal variables, okay, which holds the information of the system. Okay. Where do we use the state space modeling? Primarily, it is used in complicated or large scale systems. Okay. This particular state space modeling approach is called as the modern approach of control system. So that we have seen as the advantages of the state space modeling. We look at the drawbacks of the transfer function. Okay. As why do we go for this state space modeling over the transfer function? So we'll see the transfer functions. What it does not work, or it does not consider the initial conditions. Okay, transfer function is only defined for zero initial conditions. It discards initial conditions whatsoever. Second, the transfer function approach can be applied only to a linear time invariant system, whereas the state space modeling can be used for the time variant system as well, linear system, non-linear system as well. Third, it does not give any idea about the internal state of the system, correct? Though it considers the differential equations, but it does not consider the internal states. It cannot be applied, the transfer function modeling cannot be applied to multiple input, multiple output systems, correct? And the state space modeling can. It is comparatively difficult to perform transfer function analysis on computers, correct? Because the S domain is there, and the calculation is not straightforward, as we are using the, not any direct mathematical process, but the indirect way of solving the differential equations using the Laplace or the Z. So we'll discuss this through one example. So let's consider a mechanical system here. Okay, mechanical system, block of mass m is placed, okay, on a ground, and force F is applied. A force F is applied and it moves. It moves in the direction of force by a displacement of x of t with the velocity v of t. And one more thing that we can consider is that the friction is zero. Okay, the friction is zero. So that will give us the easy to understand how the state space modeling can be used and it's helpful. Okay. So force F is applied on block of mass m, which gives the output in the displacement as x with the velocity v. Okay. So the mathematical equation using the differential relationship can be this. Correct. M into A is equals to F. Correct. F is equals to m into A. A is nothing but the acceleration. Acceleration is nothing but the second order differential equation of displacement. The system can be characterized in another way as well. Correct. This acceleration, what is the acceleration? Acceleration is the first order differentiation of velocity. And what is velocity? It is the first order differentiation of displacement. Okay. Like this, here you can see the velocity, it's first order differentiation of displacement x of t. And what is this v? V is the first order v is the first order differentiation of x of t, and what is a, that is the second order differentiation of displacement, is the first order differentiation of velocity. Correct. So here we can simplify this to get this two terms as the first order differentiation of displacement and first order differentiation of velocity. So we got these two relationships here. Okay, f by m and v. We'll name this equation 1, equation 2. The equation 1, equation 2. Now from the equation number 2, okay, dv by dt is equals to 1 by m into f. Okay, we'll solve it for the value of v of t. Okay, so we'll get the integration on both the sides. We'll get v of t is equals to 1 by m integration minus infinity to t f of t dt. Okay, and when we do the simplification, okay, when we do the simplification, let's split this particular time interval from the negative infinity to the t, will be split it into two sections. Okay, two sections, either to the zero instant or the any instant t0. Okay, any instant t0. Okay, so it will be minus infinity to t0 and t0 to t, as the limits will be split. Okay, there will be no changes, no differentiation. Differences will be seen. But the thing is, when we consider all the data to this particular t0 instant, if it is known or it is to be at the instant is equals to 0, what we call it as, till this information up to this, we call it as the initial condition. That means we know all the values, all the history, all the information from infinity to t0. Okay, so that will give us, this will be f1 by m into f0 will be v of t0. Okay, the rest is as it is. Okay, so this is equation number 3. Now from the equation number 1, let's do the simplification. Let's integrate it from minus infinity to t. Okay, and again split it with the known time instant t0. What it will be, from minus infinity to t0, it will result into the integration of v of t as displacement x of t0. Okay, and it will be as it is. But the integration of t0 to t, the variable v of t dt, we already know this. Okay, the definition for the v of t, definition for the v of t is this. The equation number 3 gives us the definition, so we'll put it here and do the simplification. Okay, we'll do the simplification. What it will be, so x of t0 plus integration t0 to t v of t 0, okay, plus 1 by m integration of f of t dt dt. Okay, so here we'll get, here we will get the double integration of t0 to t f of t dt d tau, and here it will be t minus t0 to v of t0, because the t0 is not the variable, okay, it is the time, okay. So it is the fixed constant value, so we'll get the t minus t0 to 0. So this is our equation number 4. So we got this differential equations and we got this solution for it, okay. Now here we will see the displacement x of t. This displacement x of t, what is it? It is the function. What the function you can see here? It is the all the known values of x of t0, all the known values of velocity up to t0. Okay, if they are known, okay, we can calculate the any displacement x of t for any time t greater than t0. That means from t0 to t, we can calculate for any displacement. You can calculate any displacement to be computed if known applied force f of 0. Okay, known applied force f of t is known for t to t0, okay, t0 to t0 onwards, and provided initial velocity and initial displacements are known. So x of t and v of t are used to represent the state of the system, are what they are representing the state of the system at t is equals to t0. Okay, so they are called as the state variables. Okay, so what we can see here, the definition for state: a state of a dynamic system is the smallest set of variables called as the state variables, such that knowledge of these variables at t is equals to t0, okay, t is equals to t0, together with the knowledge of the input, together with the knowledge of the input for t greater than or equals to t0, completely determines the behavior of the system for any time t to t0. Correct. So that is the same definition you can verify here. The displacement, so we can get the any value, we can get the value for the displacement at any time from t0 to t if the f of t is known. Correct. That is the input. And we also know the input states, input variables values till in minus infinity to t0. These are the initial conditions. So said that the knowledge of these variables at t is equals to t0 and the input from t0 to t are completely determining the behavior of the system. Okay. So the state is by no means limited to any physical system. Okay, it is a mathematical concept. Okay, it is a mathematical concept. It can be used in any of the system. Next is the state variable. Okay. State variable of a dynamic systems are the variables making up the smallest set of variables that determines the state of the dynamic system. Okay. What is state of the dynamic system? The value of state variable at t is equals to t0. Okay. What is state vector now? A state vector whose elements are the state variables. Okay. Just like this. If n variables are there and x is the variable that you are using to represent the state variable, so it will be x1, x2 up to xn, and all these are the vector. Okay, if those are the elements of the state variable, then we call it as the vector. Okay. If n state variables are needed to completely describe the behavior of the given system, then these n state variables can be considered as the n components of the vector x, and those will be called as the state vectors. Okay. A state vector is thus that determines unique uniquely the system state x of t for any time t greater than or equals to 0. From t0 to t, the integration is from t0 to t. For that, it determines the system uniquely. Once the state at t is equals to t0 is given, and the input for t0 to t is specified, the state vector will be uniquely determining the system behavior. Now, what will we call the state space? The state space will call where the x's are state variables, where any space whose coordinate x's are state variables will be called as the state space. state equations. Okay. We'll discuss the state equations in the next class.